Today, we're exploring an interesting paper on test time scaling, which basically asks, what if we just let the model think a bit longer? Imagine a game show contestant who presses a big, flashing wait button whenever they need more time. That's the spirit of this paper. Instead of using complex reinforcement learning, the authors propose something called budget forcing. It's as simple as telling a model, hang on, take a few extra seconds. Then, surprise, the model's accuracy goes up. Now let's dive in.
All right, let's dive into this paper about test time scaling. The core idea is pretty straightforward. If we give a model more time to think during inference, can it reason better? Instead of relying on complex reinforcement learning techniques, like OpenAI's on-one model, this paper explores a simpler approach called budget forcing. Here's how it works. They either force the model to keep thinking by appending weight to its outputs, or cut it off early if it's overthinking. To test this, they created a dataset of 1,000 questions, called S1K, which includes reasoning traces that are carefully validated for difficulty, diversity, and quality. They fine-tuned a 32 billion parameter model on this dataset and found that their approach outperforms OpenAI's on-one preview model on competition math tasks by up to 7%. Now, take a look at Figure 1. It shows something really interesting. For tasks that require deep reasoning, longer thinking times generally lead to higher accuracy. As the model processes more tokens, its performance improves, jumping from around 50% to 60% on AMI 24. This backs up their claim that extra test time computation helps. So, why does this matter? Well, a lot of past approaches have tried to replicate OpenAI's on-one model using techniques like Monte Carlo tree search or reinforcement learning, but none have quite captured the same behavior. This work suggests a much simpler alternative. Just let the model think longer in a controlled way. The big question they're asking is, what's the easiest way to get the benefits of test time scaling without all the complexity? Let's explore that. The paper's central tool is budget forcing, which manages how much time a model spends thinking during inference. If the model is producing more reasoning steps than they want, they tell it to stop using a termination token. If they want it to keep going, they append something like wait that encourages further reasoning. They tested how best to pick those 1,000 training examples. Random choice was underwhelming. Only choosing very long reasoning traces also didn't cut it. Focusing on a balanced set of examples, ensuring diversity, difficulty, and quality turned out to be key. Different sampling strategies were tried, and performance varied based on how examples were selected. How did they build this dataset in the first place? They started with 59,000 questions, spanning multiple sources to ensure high-quality, reasoning-heavy problems. Then, they boiled this down to 1,000 examples by filtering for difficulty, diversity, and correctness. The dataset ended up small, but powerful for fine-tuning. Another interesting detail, they used Google's Gemini Flash API to generate reasoning traces for these questions. That gave them structured steps and solutions, which then trained their model to better mimic step-by-step thinking. All in all, the message here is that we might not need complex reinforcement learning if we can simply guide the model to think more effectively. It's data efficient and scalable. They continue by explaining how they refined that large pool of 59,000 samples down to 1,000 high-quality examples. It wasn't random. First, they removed duplicates or irrelevant entries, ending up with roughly 51,000. From those, they selected 384 top-notch ones by hand. These needed no extra filtering. But how did they measure difficulty? They used two AI models, a 7B parameter and a 32B parameter 1, to grade how easily each question could be solved. If both models solved a question too easily, it was considered too simple and dropped. They also looked at how many reasoning steps it required, assuming more steps meant higher difficulty. That shrank the dataset to 24,496. For diversity, they classified questions into different domains using an AI model trained on the mathematics subject classification system. That way, it wasn't all just math. They included physics, biology, economics, and more. Finally, they sampled from these domains while favoring longer reasoning traces, arriving at a carefully balanced set of 1,000 examples. Before wrapping up this section, they reintroduced test time scaling. They break it into sequential versus parallel approaches. Sequential means each step of reasoning builds on the last. Parallel means multiple chains of thought are generated independently and then combined somehow. This paper focuses on sequential because iteratively refining the model's thoughts often yields better results. They also revisit budget forcing, controlling how many tokens get generated, forcing the model to finalize answers at the right moment, or prompting it to keep going if it tries to stop too soon. This ensures the model actually uses its allotted compute time efficiently. Now let's talk more about how budget forcing helps models rethink their answers. In Figure 3, there's a neat example. The model is asked how many times R appears in the word raspberry. It quickly but incorrectly says 2. Then budget forcing steps in and says, keep going. So the model double-checks and realizes the correct answer is 3. Without that push, it would have stopped early. To quantify test time scaling, the paper defines 3 metrics. First up, control. How precisely can we limit the model's compute usage? If we set a range for how long the model should think, does it stick to that range? Next, scaling. Does performance actually go up when we let the model think longer? If that line slopes upward with extra reasoning steps, that's a good sign. Finally, performance, the highest accuracy the model achieves on the benchmark. They compare budget forcing against other methods. One is conditional length control, where we tell the model upfront how many tokens or steps it should generate. Another is rejection sampling, where you generate multiple responses and then pick the best one based on length or other criteria. They fine-tune a 32 billion parameter large language model, LLM, using just 1,000 examples. This training runs for only 26 minutes on 16 NVIDIA H100 GPUs, so it's fast and scalable. For their experiments, they focus on 3 challenging benchmarks: AIM-24, competition math; Math 500, another math dataset; and GPOA Diamond, a high-level science reasoning benchmark. These tasks demand multi-step, logical thinking. Here, they dig deeper into test time scaling results. Check out Figure 4. In the first experiment, the model takes on competition math problems. Typically, it stops reasoning after a certain point. But by forcing it to keep reasoning, accuracy rises significantly. That's evidence that the model sometimes stops too soon, and a gentle nudge to keep going can boost results. In the second experiment, they compare sequential versus parallel scaling on tricky PhD-level science questions. With sequential scaling, each new thought builds on the previous one. With parallel scaling, they generate multiple answers independently and do a majority vote. Sequential scaling wins big, hitting 60% accuracy, while majority voting lags behind. Now, take a look at Table 1. They stack up their models 1 to 32B against other well-known ones, including OpenAI's O1 Preview, QN, Gemini 2.0, and Sky T1. Considering S132B was trained on only 1,000 examples, it holds its own remarkably well in terms of sample efficiency. In fact, it outperforms some models that had way more data. That's a powerful demonstration that you can achieve competitive performance with a small but well-crafted training set. They also run additional comparisons. Since Gemini doesn't publish official evaluation results, they manually feed it questions via its web interface. This ensures a direct, fair comparison with S1 to 32B. Overall, the point is that forcing models to think longer can significantly improve their reasoning, and S132B does that with minimal fine-tuning data. This section emphasizes a crucial takeaway. More thinking time helps up to a limit. In Figure 4, you see budget forcing push performance higher on AIME24, but after about 6 cycles, the gains taper off. So there is a ceiling effect. They also reaffirm that sequential test time scaling beats parallel approaches. Instead of generating multiple guesses and picking one, it's more effective to refine a single chain of thought iteratively. They compare S132B to other models, like QN 2.5 to 32B Instruct and R1 to 32B. Even with just 1,000 training examples, S132B can outperform these alternatives, which have way more training data, sometimes hundreds of times more. Then they explore why S1K, the 1,000 example dataset, works so well. In Table 2, different dataset selection methods are compared. Random sampling? Not so good. Choosing the longest reasoning traces? Helps in some places but harms others. The best strategy is a carefully curated mix of quality, diversity, and difficulty. Is more important than simply having a big dataset. Finally, they show how different ways to cap test time computation perform. Table 3 indicates that budget forcing checks all the boxes: perfect control, smooth scaling, and top accuracy. Just telling the model to wait when it tries to finalize too soon outperforms other methods like fixed token limits or step-based stopping. In a nutshell, S1 to 32B's success is about smart data and clever inference control, not brute forcing with more data. Now let's look at some real examples of S132B in action. They show how it tackles advanced questions in game theory, linear algebra, and quantum mechanics. First, there's an AIME24 question where Alice and Bob take turns removing tokens. You want to find the number of starting positions where Bob has a guaranteed win. The model figures out a pattern for losing positions, multiples of 5 and multiples of 5 plus 2, and concludes there are 809 losing positions. That's a subtle combinatorial argument, and the model nails it. Next, there's a classic linear algebra problem about vector projection. The model does the dot product, computes the magnitude, and then scales appropriately. It ends up with a correct projection vector. Finally, the quantum mechanics example involves solving for the energy spectrum of a particle in a 2D potential. The model starts by translating the potential from polar to Cartesian coordinates, sets up the Hamiltonian operator, and applies the Schrödinger equation. The result is the correct energy spectrum, showing that it can handle pretty sophisticated physics. So these examples show S132b isn't just regurgitating facts, it's doing real, structured reasoning in a variety of domains. Here, they shift focus back to budget forcing and rejection sampling. In Table 4, they ask a fun question. Does it matter which word you use to keep the model thinking longer? They tried wait, and similar cues. Wait emerged as the best performer, simply appending that one word significantly boosts reasoning accuracy. Meanwhile, rejection sampling is a different strategy. Let the model generate multiple answers, then choose the best. Figure 6 shows a surprising result. Letting the model produce longer responses doesn't always help. In fact, the longer it goes, the more likely it is to introduce confusion or mistakes. Shorter, more focused answers are often better. They then address why training on just 1,000 examples can be so effective. Section 6.1 explains that modern models already see huge amounts of reasoning data in pre-training. A small fine-tuning set can steer them in the right direction. This relates to theories of superficial alignment, where a little guidance can have a big impact. Finally, they bring up benchmarks and other methods in the literature. From Olympiad math to chain-of-thought prompting, many approaches aim to boost a model's reasoning. But this paper shows it's not all about scaling bigger. Strategically chosen data and controlling test time behavior can have a huge payoff. Now they revisit test time scaling more broadly. Should models reason sequentially, refining their answers step by step, or in parallel, generating multiple answers and then picking the best one? Take a look at Figure 7 here. It compares different approaches. A method called rebase, which uses a reinforcement-based reward model, outperforms both majority voting and purely sequential methods. It balances exploring new thoughts and pruning unhelpful ones. That means it doesn't waste too many tokens on fruitless tangents. Sequential scaling is still good, but it hits a plateau. When you push it too far, context window limits kick in, and the model can't juggle so much information. That's a hint that parallel or more advanced strategies might help at very large scales. They also talk about potential future directions. What if we vary the prompts, alternating between words like wait and think again? What if we adjust frequency or temperature settings to keep the model from looping? And of course, reinforcement learning is another path for fine-grained test time control. Toward the end, they reflect on why this all matters. Better reasoning models can impact everything from daily productivity to scientific breakthroughs. But there's a flip side. The leading players like OpenAI's R1 or DeepSeek's R1 often don't share details, making it harder to build on their work. So the authors emphasize that open, reproducible research is essential for progress. That's the big picture. Scaling up test time reasoning is promising, but we need careful methods, good data selection, and transparent practices to unlock the full potential of these models. Thanks for joining us today. Happy learning and stretching together.